For problem 2, we will find the capacitance for a spherical capacitor. So by definition, the capacitance is charge divided by difference in the electric potential, delta V, and absolute value. So how to find the capacitance? We have two conducting spherical shells. Inner radius of this shell is A. Inner radius of a larger shell is B. And the thickness of each of them, let's call it T. Two conducting spherical shell, and we need to find the capacitance. So I charge this spherical shell with charge plus Q. And we know that if we charge a conductor, then the charge will be on the surface of this conductor. So what we basically are interested in, we are interested in the outer surface of this inner shell. Now if I charge it with plus Q, then there will be minus Q induced on the inner surface of the outer shell. And there will be electric field in radial direction. I will do it in red. So there will be electric field from plus to minus in radial direction between these two plates. And this is the electric field we are interested in, because we need to find delta V. What is this delta V? Delta V is potential at point B, at RB, not at point, at RB, minus potential at A plus T, where plus Q is, V at A plus T. And this is our delta V. This is equal to minus integral from A plus T. This limit comes here, this limit comes here. And here I have E dot dr. And we understand that electric field from symmetry, it is radially out. So my E, it has just radial component. So I will rewrite this integral A plus T to B. I rewrite E dot dr is electric field in radial direction, ER dr. IR dot IR, unit vectors in radial direction will give me 1. So what we need to find? We need to find the electric field between the plates of this capacitor. And to find the electric field, I will use Gauss's law. Gauss's law tells me that the flux of the electric field out of closed surface is equal to the charge enclosed over epsilon naught. So which Gaussian surface we will choose to solve the problem? I will use blue for the Gaussian surface. Obviously, we will use symmetry, and our Gaussian surface will be a sphere that we will put somewhere between inner and outer shells. So what will be the flux of the electric field out of my Gaussian surface that has arbitrary radius r? The electric field is radially out, and the area vector for this Gaussian surface is also radially out. So electric field is in the same direction as area vector, which means that my dot product E dot ds is just product E times ds. E times ds. From symmetry, electric field is the same at each point of my Gaussian surface. There is no specific direction. I take E out of this integral since it is constant, and integral ds is S, where S is area of my Gaussian surface. It is 4 pi r squared. This is the left-hand side of Gauss's law. Now I have 1 over epsilon naught Q enclosed. What is the charge enclosed by the Gaussian surface? It is just Q, charge Q. So what I have on the right-hand side of Gauss's law is Q divided by epsilon naught. And we immediately derive the electric field. So what is the electric field between these spheres? It is 1 over 4 pi epsilon naught Q over R squared. This is the magnitude of the electric field, and the direction is radially out. Radially out. Now I take the electric field and I bring it here under this integral. So let's keep this going, and we have minus integral from a plus t to b. ER is 1 over 4 pi epsilon naught Q over R squared dr. It is minus Q over 4 pi epsilon naught. Those are constants. I take them out of integral. And integral dr over R squared is minus 1 over R. And the limits are from a plus t to b. Now I plug in the limits, minus and minus plus, so I have Q over 4 pi epsilon naught. Upper limit gives me 1 over b, and lower limit gives me 1 over a plus t. Now we know delta V, and we are ready to bring it back into capacitance and find the final expression for the capacitance. So this is B, let me bring it here. Q over delta V, Q, and then divided by delta V, absolute value, which gives me Q, 4 pi epsilon naught, come to the numerator, and then 1 over B minus 1 over A plus T. Q and Q cancel out, and we have our expression for the capacitance for a spherical capacitor. 4 pi epsilon naught divided by 1 over B, where B is the inner radius of the outer shell, and then minus 1 over A plus T, and we have to take absolute value. Capacitance is positive by definition. Let me write it a little bit better. Here, minus 1 over A plus T, absolute value. So we found the capacitance for a spherical capacitor. It is right here. And we followed the same steps. We wrote the definition of the capacitance. Then we found delta V. And then we found the electric field using the Gauss's law. We used the electric field that we found from Gauss's law to calculate delta V. And then we bring everything back into our expression for the capacitance. And the capacitance depends just on the geometry. Does not depend on Q, does not depend on delta V as expected.